Здравствуйте, друзья! Добро пожаловать на канал Sudoku+, где мы знакомимся с лучшими головоломками мира и изучаем методы их решения. И сегодня у нас очень необычный выпуск. Один из наших подписчиков, Сергей, прислал ссылку на замечательный пазл, который канал Cracking the Cryptic предложил в качестве соревнования на то, кто предложит наиболее элегантное решение этого пазла. Ну, я решил совместить приятное с полезным, записать этот видеоролик с решением этого пазла и для вас, и для канала Cracking the Cryptic. Вот этот пазл. Посмотрите, я пользуюсь программным обеспечением канала Cracking the Cryptic. Значит, что в этом пазле нового? Ну, во-первых, здесь действует правило классического судоку. Во-вторых, здесь есть вот такие вот дополнительные регионы, то есть это судоку с частичными суммами. И плюс есть еще вот такие вот цифры со стрелками. Это называется диагональные суммы, по-английски little killers, то есть маленькие убийцы почему-то. И эти цифры показывают сумму цифр в соответствующей диагонали. То есть вот в этих двух клетках сумма цифр будет равна 5. В этих четырех сумма цифр 9. В этих сколько здесь? В 7 клетках сумма цифр равна 50. Притом вот в диагоналях, в отличие от вот этих вот дополнительных регионов, цифры могут повторяться. Ну а сейчас я переключаюсь на английский язык. Hello folks, here's my solution. Okay, the beginning is trivial. We have this 5 little killers, and in the marked cells there can be only 1, 2, 3, and 4. Now we have this 9 little killer, so the sum of those two cells cannot be less than 5, otherwise the marked 4 cells will be less than 10, which is absolutely impossible. So if those cells are less than 5, then these cells are cannot be more than 4, so we can put 1, 2, or 3 here. Let's look at those cages, 4 cages. So they are very much restricted. The numbers are pretty big. And if we ask where can we place 1 and 2 in the central box, they cannot go here, neither here, neither here, because in those cages the remaining 3 cells will sum to a number more than 24, which is impossible. So 1 can go here, not both, because this 25 cage will break. So there should be 1 or 2 in the central cell, and the other one goes here. Now we will ask where the 3 goes in the central box. Now it cannot go here, not here, not here, not here, because 1 or 2 is already there, and 3 plus 2 is too little. So it can go only into the 27 cage. And now the remaining cells sum to 24, so we know exactly the contents of this cell. It's 3, 7, 8, and 9, and 3 cannot be here. For the similar reason, 4 can go only into the 28 cage, and the same story. It can be only 4, 7, 8, and 9. No 4 here. 5 can go now only into the 29th cage. So we know that this 29 cage contains 5, 7, 8, and 9. no 5 here. Now where 6 goes? The 6 goes only to the 25 cage, and it cannot be accompanied with 2, because it's going to be 8, and the remaining cell with 1, because the remaining cells will sum to 18, which is impossible. So it can be accompanied only by 2. And now we know that the central cell contains 1, and here we have a 8-9 pair. Now the easy part is over. The main issue with this puzzle is that this 50 diagonal is, of course, it's a bit restricted, but not that much, because we already have big numbers in those 3 cells, so there are thousands of different ways to fill in this diagonal. Plus, please note that all the other little killers do not affect big numbers anyhow. Big numbers, I mean 7, 8, and 9. Because 7, 8, and 9 obviously cannot go into this 9 diagonal, and 5 diagonals either. So basically speaking, even if we solve all these small little killers, 5s and 9s, we will have no idea where to put 7, 8, and 9, or to be exact, how to distinguish between 7 and 8 and 9s. And in the central area, apart from this 8-9 pair, 7s, 8, and 9s are absolutely symmetrical, so we can put them in any order in those 3 cages. So that's what I call delayed clues, because we cannot use any clue directly right now to understand where we put how we arrange 7s, 8s, and 9s on the grid. So this is a well-known idea that can be executed in 3 different ways. One way is to put arbitrarily numbers like anywhere 9, 7, and 8, see what happens, and then if there is a contradiction, we just sweep them with each other. Here, this idea, I don't think it works well, because there's a non-symmetrical 8-9 pair here. The other way is to substitute 7, 8, and 9 with some other 3 symbols, for instance, letters ABC. Here, first of all, I cannot use ABC in this software, and secondly, I'm not sure that this is going to be very sufficient, or, well, it can be very sufficient, but I know a third way, and third way is to use colors. So I will use 3 colors, yellow, green, and red, to mark all cells where 8, 7, or 9 have to go, and then I'll try to color as much grid as possible, and then using this 50 little killer clue, I'll try to understand which color belongs to which number. So I call it traffic light. The strategy, I call it traffic light. Guess why? So look, here all the numbers are very much connected to each other. So they, if for instance I put, let's say, I don't know, yellow here, so this means that this whatever goes to this two cells 7, 8 or 9, I call it yellow color. So then the yellow 7, 8, the yellow number will go here and here. So basically these three yellow numbers, they are mirrored, so they have to be identical. The same story with, for instance, red. So whatever goes into these two cells 7, 8 or 9, it's going to be red. And then this cell is red and this cell is red. Okay, and now we have green for this pair of cells, and then this cell is green and this cell is green. And look, we already have a result, because if I put a green number, big number, into this cell, then the mirrored number will be here and they see each other, which is impossible. So here can be only 5, and now the green number will go here for sure. Okay, so the next step, I want to study these two columns and these two rows. Let's mark them gray. Question: how many big color numbers can go into gray cells? So in each row or column there are already at least or definitely 2 color numbers. So in each row or column marked gray, there can be only one additional color number. So the total number of color numbers in gray cells cannot be more than 4. It can be less, by the way. So if, for instance, we put a color number into this crossing, then we'll have only 3 numbers. And if we put color number somewhere here, then we'll have only, well, here you cannot put color number, but anyway, if we could, there would be only 2 color numbers in 2 columns and 2 rows. But what is important, their number cannot be more than 4. And now let's look at the corner boxes. There are exactly 12 color numbers, 7s, 8s and 9s in those 4 boxes. And in the gray cells there can be only 4. So the remaining 2 by 2 boxes have to contain 8 color numbers. And the only way to do it is to put color numbers into those cells. So these cells can contain, 7, 8 or 9 only. Moreover, I already said that if we put any color number in this one of these crossings, the amount of color numbers in the gray cells will be less than 4. So we cannot have 12 color numbers in the corner boxes. So they cannot be color numbers. Let's mark them blue. And those 4 cells, if we put any color number here, it will remove color number from corner boxes, and then we'll have less than 12, which is impossible. let's also mark them blue. So my point is that in blue cells you cannot have any of 7, 8 or 9. Now let's look at 5s and 6s. In each of the corner box we need to have 1 5 and 1 6, and this 2 by 2 square cannot have either 6 or 5, so they can be only in these areas. Let's put arbitrarily for instance 5 in one of those 3 cells. Then we'll have 5 somewhere here, somewhere here, somewhere here, and here we cannot have a 5. Same story with, or I could put them here and get the same distribution of 5s here, here, and here. So the main idea is that however I put 5s in those gray cells, they cannot be in blue cells. And absolutely the same story with 6s. So 6s also cannot go into blue cells. I could get it using a different technique, which is called the jellyfish pattern. So if we look at rows 1, 2, 8, and 9, there are only 4 places where we can put 5, and this is a jellyfish. So in any cells which belongs to columns 3, 5, 6, and 7, there are no more 5s, so the blue cells cannot contain 5. Same story with 6s, but in rows. Let's mark them red. Okay, red already used, so let's mark them, I don't know, gray. So here we cannot have 6 because of this 6 pair. So in columns 1, 2, 8, and 9, we can have 6s only in those 4 positions, in those 4 rows. So in rows 3, 5, 8, 6, and 7, 6s cannot go anywhere else, which means that 6s cannot go to blue cells. So you can use either technique, and in any case the result is the same. 6s and 5s cannot go to blue cells. Now, what can go to blue cells? Cannot be 8, 7, or 9, cannot be 5 or 6, so it can be only 1, 2, 3, or 4. And this is crucial, especially this one. Okay, let's return to our 5 little killers clue. We don't know how they're going to be solved. So there's in each box there can be only 1, 4 or 2, 3 pair, and at the moment we don't know how they're going to be distributed. But what we know for sure is that those pairs which see each other, so which share the same columns or rows, cannot be the same. And the reason is, for instance, what if these 4 cells are the same, say 1, 4 pair? Look, 1s and 4s now filled now belong to columns 8 and 9, and in this box we cannot put any 1 or 4 in those 6 cells. So 1 and 4 goes into those 3 cells. But there is only one cell which can have 1 or 4. And the same story, look, here we have only one cell, here only one cell, and here only one cell. So the idea is that they have to alternate, which means that if, for instance, here we have a 2-3 pair, then there will be 1-4 pair here, 2-3 pair here, and 1-4 pair here. So they are repeated diagonally, not vertically or horizontally. This is very important. Now let's look at this 9 little killer clue. First of all, I think 3 is impossible here because we have 3 locked in the central box. And for the same reason 2 is impossible here. Now, question: can those 2 cells both contain a 1? The answer is no. Why is that? Look, if it contains a 1, if both contain a 1, then we're going to have a 2-3 pair here. And we just said that that means that those 2 pairs are going to be 1-4 pair. And because we already have 1s here, so 1 will go here. And in this box there is only one place for 1 now, here. Now we have 9 clue -1 -1, so those 2 cells sum to 7. But how are we going to make 7 without using 1, 2, or 3? This is absolutely impossible. So the answer is either of this cell, we don't know yet why, which one has to contain other digit than 1. So it can be either 1 or 3, or 3 and 1. So if it's 3 and 1, the remaining 2 cells in this diagonal sum to 5. So they have to consist of 1, 4, or 2, 3 pair, and they form a quadruple with those two cells. But now we have another cell, 5th cell, which also contains 1, 2, 3, and 4. 5 cells cannot contain 4 digits, so this is absolutely impossible. This arrangement cannot happen. So the only arrangement which is possible is when we have 1 here, 2 here, and now we have 2 cells summing to 6, and we cannot use 2 and 4 because in this case we took both options from this pair. So the only way to form 6 is to use 1 and 5. And now, as Simon says, we're cooking with gas. Because now look, we already used 1 here, so now we have only one option for this pair. It has to be 2 and 3. And we have 2, so this cell is 3, this cell is 2. Now look, this cell now can only be 4. Let's tighten some pencil marks. This cell cannot contain 1 and 4. This one cannot contain 4. This cannot contain 2 or 4. No 4 here. So as we have both 2's here, this pair has to be 1 and 4. Okay, now look, and by the way, if it's 1 and 4, this has to be 2 and 3, and this has to be 1 and 4, and we have 1, so 1 goes here and 4 goes here, and we can tighten our pencil mark a bit more. So now this cell cannot contain 1, and we've got a 2-3 pair here, which is absolutely useless, of course. But what is not useless? Look, we have a 2-6 pair here, so in the box 4, 2 can only be in those 4 cells. And look, in box 7, 2 can be only here. So where the 2 goes in column 3, only in those 3 cells, and here we have 2 2's, so 2 can go only here. And we continue to tighten pencil marks. Now, where does the 3 go into box 2? We have 3's here and 3 here, so it can go only into those 2 cells, and now it can go only into 2 cells in box 1. And we have the same story with the 3's. Where 3 go into box 4? Only here. And suddenly we opened this we know now where the 3 goes into this cage. Now it can be uncolored, and here we have a definite color number. Okay, let's continue. Now we have 1 here, so this pair now is disambiguated. Sorry for my English. Now it's 5 1, and now we open this pair. What else? We've got 3 here, so it cannot be 3, by the way, long ago. Now here we cannot have a 3. Now let's look at box 6. Where can 5 go? Only this cell. Same question about 3 in box 6. Now it goes only here, 2 goes here, and in box 9 3 can go only into this cell. So now we tighten our pencil marks, and now we get 1 4 pair, which is also absolutely useless. But anyway, let's continue. Okay, 1. Look, in box 4, 1 can go into one place only. And now there's a very interesting observation in box 6, or this cell to be exact. Look, now this cell cannot be a color cell because all three colors see this cell. So it cannot be 7, 8, or 9. By classical Sudoku, it cannot be 1, 2, 3, 5, and 6. So the only digit it can be is 4. It's actually it's a naked single. So now remember, we have locked 4 here, so in box 4 can go only into those cells, into this cell. 5 can only go here, 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 and here. Now we have 2 color numbers in box 6. Where does the third color number go? It cannot go here, because in this row 6 we already have 3 color numbers. So the only place it can go is those 2 cells. Which one we don't know exactly, but we color them all. So this is this 2 cells colored red means one of them is going to be a colored number red. So now in box 4, red can go only into those cells, making this virtual pair with 5. Sorry, not red, green, of course. And the remaining 2 cells is a pair 2 and 6. And here we also have a 2, 6 double. Now here also we have a double 6, 7. Now there's a wonderful classical Sudoku technique which I'm gonna use just for a change. It's called X cycle, or to be exact, this is a one way of execution, the X cycle. It's called string kite. So if you look at 6s at row 9, column 9, row 6, and box 6, let's mark them gray. We see that in in column 9, row 6, there are strong links, and this structure is called string kite. And basically it's a part of X cycle technique. And what it means that all cells which see both these end cells, actually there is only one cell here, this cell cannot contain a 6. You can look at different way. You can use open rectangle, because if you take this strong link and this box number 4, where 6 can go, only here, you see that if this is a 6, then this is going to be a 6. If this is a 6, then so in both solutions this cell cannot be a 6. Okay, so obviously this can be solved without any classical Sudoku diabolical techniques, but in my solution this is important. Now first time in this solution I look at this 50 clue diagonal. First of all, just let me notice one important thing. that if we try to put big numbers into those three cells, big numbers 7, 8, or 9, they all have to be different, because here we have green color, here we have only yellow color possible, and here only red color possible. But if we put, of course, maximum green, yellow, and red into these three cells, then we're gonna have all colors repeated twice. So the sum of these 6 cells is going to be 48, and we will have to put 2 here, which is absolutely impossible. And by the way, these 3 cells, they are all different colors, which means that they contain all 3 numbers 7, 8, and 9, and the sum of those 3 cells is going to be 24. Now, question: can this diagonal contain a 3 here? The answer is no. And the reason why it is impossible is because what happens if we put 3 here? First of all, can this cell contain a 5? No, because the sum is going to be of those 5 cells is going to be 32, and then the sum of those 2 cells is going to be 18, and it's absolutely impossible. We cannot put 2 9s because, remember, those cells can be different color only. So if we have 3 here, we cannot have 5 here, which means 5 goes here, and we have a green cell here, and we have 7 here. But look now at column 2. Now we have 1, 2, 3, and 4 big numbers in 4 cells, which is absolutely impossible. So what we can conclude, 3 can go only here. And this is a big this is a breakthrough, a small breakthrough. Now we can finally open this pair, 2, 3. Now 6 goes here, 2 goes here, and here. By the way, let's uncolor those gray cells and return this red one. Now we have 6, 7 double here. Now another thing I noticed, that 5 cannot be in our diagonal, and this is a little bit more complicated, but let's try to put 5 here. First of all, please note that 5 has to go here, and now in this diagonal, this is going to be green, and in this diagonal we already have 3 big numbers, so this is going to be 6, 7 here, and 6 here, and 6 here. So now in our 50 sum diagonal, we have 5 cells summing to 35, and the remaining cell have to sum to 15. That's why 5 is not possible here. 5 can only go here, and here we have a red number. But now we have a problem. Look, in this row 7, there's only one remaining cell which has to be yellow. And now question, what do we put into this cell? It sees all three colors, green, yellow and red, and it's 7, 8 or 9, so it has to be green, yellow or red. This is impossible. So that's why 5 cannot go into our diagonal, and 5 has to be here. And here we have a green cell, so we can put 7, 8 or 9 here. Now 5 goes here and cannot be here. Another observation is related to this very bottom right cell. Which color can it be? Can it be, for instance, red? Look, then this cell is going to be red, not this one, and this cell is going to be red. Now 6 can go into only this cell. By the way, 6s here are limited to these two cells. I could have put here earlier. So if this is red, this has to be a 6. And now look at this column 9. Where do we put color numbers? There are only 2 cells available. This one cannot be color because we already have 3 colors in this box 6. So this is impossible. Can it be now yellow? In this case, in row 7, there is only one place for yellow cell. It's here. And now look at in box 1, there is only one place for yellow cell, here, and in box 3, here, because we already have 2 yellow cells. And those 2 yellow cells see each other, which is impossible. So my point is that this cell can be only green, can only be green. By the way, let's uncolor these blue cells. We don't need this color anymore. And now this is huge, because look, in box 7, the only cell which can be green is this one. And now where can we put 1 in this box? Only here. 4 goes here. In box 2, 4 can go only here. And now we finally disambiguate this yellow pair. So now 4 can go only here, and here we have a normal yellow cell. In box 7, 4 can be placed only here. Okay, let's move on. Now in box 3, this is gonna be a green cell. Look, in column 3, we already have all 3 colors, so this is gonna be 5 and 6, which means this is gonna be 7, this is gonna be 6, this is gonna be 6 and uncolored, this is gonna be yellow, this is gonna be red, now this is gonna be red, and this is gonna be I switch to central notation 5 and 6, and this is gonna be yellow. This is gonna be green. What else? This is a 6, and now we have just a second. Yeah, in box 2 there is only one for green cell. It's here. And please note that green cell cannot be 7 because it's either 8 or 9. Now in box 7, where the red cell goes, only here, which means 7 is yellow, and we got our first color defined. So now we can remove 7 from all green and red cells and put 7 in all yellow cells. Here we go. So now this cell is red, and basically, okay, this is yellow, so this has to be a 7, and basically the only two cells we don't know form this X-wing pattern for 7s. It's just a wonderful picture. Now this cell, this cannot be a color cell anymore, because we already have 3 colors in row 8, so it can be either 5 or 6. And we need a final step. Now look at our diagonal. We have 7, we have 24, 31 total. We have 8 or 9, so it's 39 or 40 total. So the remaining 2 cells sum to either 10 or 11. But look, they cannot be different, because otherwise, if they are different, this cell is broken. This cannot be any of 2 numbers. So they have to be either both 5 or both 6. If they are both 6, the sum is 12, but we need 10 or 11. So they have to be both 5. And now we need 9 here to make the sum equal to 50. And now we know everything. Now we can color, we can make all green cells 9, all red cells 8, this one is 6 now. Okay, where 5 goes into box 2, only here. 3 is here, 7 is here, and we know final big number allocation. Let's mark it yellow, just for the beauty of this picture. So this one now is 6, this is 5, 6, now this pair is known. Now here we have 1. So what do we put here? 3, 2, and finally 6. And here we go. Wonderful puzzle. Pretty difficult one. I would say very difficult one. I'm not sure this is the most elegant solution, but I couldn't find a simpler way. So here you are. Thank you. Bye-bye. Ну, я переключаюсь снова на русский язык. Значит, решили мы этот сложнейший пазл. Сами понимаете, что решал я его не вживую. Вживую такой чудовищной сложности пазл решить невозможно. Если вы немножко понимали, о чем идет речь, то я тут применял массу всевозможных стратегий, техник, методов, которых мы вообще еще даже не изучали на нашем канале. Там у нас даже там Jellyfish попалась, медуза, у нас попался X-цикл, это из классического судоку, на методов, которым решаются вот такие вот разные хитрые, сложные судоку, вариантные, здесь вообще не перечесть. Ну, а я на сегодня с вами прощаюсь. Ставьте лайки, пишите комментарии, подписывайтесь на наш канал. Мы скоро увидимся уже в нормальном русскоязычном формате. До свидания.